Popple. I am very delighted to be here, and also thanks to SIGPlan for the award. I'm very honored to be honored in this way. So today I'm going to talk a little bit about the influence of dependent types, and what I mean by that is I want to answer the question, how has dependent type theory influenced the design of the Haskell type system? So I've worked a lot on the Haskell type system, and so I can give you a very short answer. It means that my code often starts with a very long preamble like this. Now, in the Glasgow Haskell compiler, language extensions must be enabled. They're not there by default. And for me, if you add some set of extensions like that, that enables dependently typed programming in Haskell. And what I want to demonstrate to you today is just how these extensions can work together to provide something new for Haskell programmers. Now, I've had a role in some of these extensions, so I can say, yeah, definitely these extensions, some of them were directly inspired by dependent type theory. Some of them came to Haskell, though, from other sources, and I think it's very illuminating how they all work together. So my goal for this talk is to kind of walk through some of these extensions and show how they fit together. And I'm going to do that mainly through an extended example. Thank you. I'm going to do that through an extended example. We're going to walk through a program that is programmed in what I call a dependently typed style. My other goal in this talk is to kind of answer the question, Stephanie, you're interested in dependent types. Why are you working on Haskell? Why not Agda? Why not Idris? Why not Lean? There's lots of great dependently typed languages out there. And I have a lot of answers for this question, too. Some of it, Haskell has an existing ecosystem and code base, so it's really fun to see how ideas of dependently typed programming fit into that code base. Some of it is that I can take advantage of features that exist in Haskell, and you're going to see some of that in this talk. Some of that you may not see in this talk is that I really believe that we should be studying language ideas, not languages. And one of the most important things of studying language ideas is to see how they transfer from languages to languages. And then, but really the biggest answer I have for this question is the set of awesome collaborators that I get to work with on GHC and thinking about the Haskell type system. Okay, so why am I interested in dependently typed programming in the first place? So my answer for that today, there's lots of answers, but my answer for that question today is that I want to be able to create domain-specific type checkers. I want type checkers to check invariants of my program so that I don't have bugs. Those invariants might be tailored to the application that I have. And so the example I'm going to show you today is a domain-specific type checker. It's a library, and it's a library for regular expressions, but it has a type system that's going to work for those regular expressions. So what do I mean? What would a type system for regular expressions look like? There's lots of ways we could design this. Well, here's the problem that I want to do. So say I have a string, it looks like this, it's a file path, and I want to use a regular expression to recognize that file path. And I want to be able to extract parts of it using this idea of capture groups in regular expressions, an extension of regular expressions where you can mark subgroups in the regular expressions and find the strings that match that part. So for example, I might want to pull out the base name of that file path, or I might want to pull out that extension, even though maybe the extension's there, maybe it's not. I want to find it if it is. Or maybe there's a set of directories in that file path, and I want all of the strings that are the directories of that file path, right? And so I want to get all this information out of that string, and I want it to come back to me in some kind of data structure. And the type system is going to come into play because the type system is it's going to guard how I access that data structure. It's going to make sure that I'm using that data structure correctly, right? And so I do have an implementation on GitHub, of course, right? I will say I've spent as much time coding in preparation for this talk as I have making slides and adjusting fonts, which is absolutely fun. But if you want to see any of the code that I show you, you can take a look at it. Okay, so and I'm going to show you a demo of this code in just a minute. But before I show you that demo, I want to walk through the regular expression that I'm going to use to deconstruct a file path that we just saw. So what does a file path look like? Right, so maybe it starts with a slash, maybe it doesn't, depending on, if it's top level or not. Then we have the next part for the directory structure, right? And here's where we have that capture group. Right? We have any number of directories, all the directories in with a slash, but the directory name itself is a non-zero list of characters that doesn't include a slash, and I've captured them. I'm using Python syntax for capture groups. It's not the prettiest, but the question mark P says that this is a capture group, and then in the angled brackets, that D is the name of the capture group. After I've captured this group, I want to refer to it as group D for directories. Right? And similarly, for the base name, I have another capture group. For this one is called B, and the base name is any sequence of characters that doesn't include a slash and also doesn't include the dot character. And then finally, I have the extension at the end. It may or may not be there, so it has a question mark for that part of the regular expression. And it is also listed with a capture group. And the extension must start with a dot, but then it's any number of characters afterwards. So this is the regular expression that I'm going to use. Again, I'm using Python syntax because I needed a syntax for regular expressions. It's not quite the same semantics as Python, though, because I'd like to get all of the directories, right? Usually with capture groups, the semantics is you only get the most recently captured one, but I can get them all. The other thing is often capture groups use numbers to indicate which one you want. I wanted to give them names, so I like to refer to things by name. Okay, so let's switch now to Haskell and see this code in action. Okay, so here you can see I have my regular expression. See if I can, right? It doesn't quite all fit on a line, but this is inside these brackets here. I have exactly that regular expression that I walked through on the slides. And then the next line here is the file name that I'm going to match, and here is the call to the match function, where I'm using the regular expression against that file name. And I can load that into GHCI. Let's see if I can get down to the other window. And I can say, let's look at the result. What are we going to get? Right? And you can see that the regular expression matching succeeds. We're going to get a maybe or an optional result from our matching function. It succeeds because we know we got a just. And then inside the just, we have this, it kind of looks like a record, but it's a data structure that's defined by my library that's giving us all of the results. Now going back up to the code up here, let me just show you. I've actually named that result. I pull it out of the just, and we can also access parts of that result by using this overloaded get function. So the get function can pull out the different parts of that dictionary, right, that record by name. So if I go down here, you can see if I ask for the base name, I can get it. And if I can ask for the directories, I get that. And then down here, now say I go to my file and I ask for something that's not in the dictionary, right? There was no capture group named F in that regular expression example. We only had base name, extension, and directory, right? So now let me try to load the file with this new line, right? And we see we get an error message. Let me go up so you can see the entire error message. And it says, look, hey, Popple17, I can't do that, right? So that's a compile time error message that is tailored for my application that tells me exactly the information that I need, right? I was trying to access the field F. it's not in that data structure. Right? And so that's exactly what I mean by an application-specific library, an application-specific type system. Right? So for the next part of the talk, I want to show you how this works. Right? How did I implement this in Haskell? And so I'm going to walk through this implementation, and I'm going to analyze it with respect to the features of dependent type systems that go into building this application. And I'm not going to do this monolithically. I've divided what it means to be a dependently typed program into 4 different aspects, right? Because this word dependent types, it means lots of different things to lots of different people. And I want to be more precise. When we're trying to look at language features, I want to hone in on the smallest thing that I can. So I've divided up the different features that I'm using in this application, and I want to talk about them individually. Of course, they're related to each other because they all work together for dependently typed programming. But we can kind of dissect this process a little bit and talk about it piece by piece. Okay, so the first thing I want to talk about is type-level computation, right? And the first part of designing a domain-specific type system is being able just to gather the information about your domain, right? And so this implementation I didn't write down any type annotations in my code. I showed you the entire code in that buffer except for the flag, the language extension flags at the top and the module imports. You saw all the code in that buffer, right? But the types are very rich. In fact, I should have told you the types because the types are very informative about this implementation, right? So if I had shown you what the type of dict, this is what it would look like, right? It's not just, sorry. Right? It's not just an opaque dictionary data structure. It's a data structure that's indexed by some type level data, some type level information. So we have that dict type, but then the argument to the dict type is a type level list, right? And that list tells us about the regular expression that we used. It tells us that it has 3 capture groups. And within those 3 capture groups, we have some information about where those capture groups appear in the regular expression. So the base name appears exactly once, right? We know any successful match of this regular expression will match the base name once. There has to be a base name in a file. The extension may or may not be there because there's a question mark. So the extension is optional. And then the directories that we match, we don't know how many of those there will be. So the type of our dictionary tells us that there may be many directories that we get as our result. How did dict get this type? Right? How did we figure out that this was the type of the dictionary? Well, the type of the dictionary came directly from the type of the regular expression. It came directly from the type of path, which says, I'm a regular expression that binds these capture groups in this way. And then the match function just makes that connection. It says that whatever regular expression you use, the result you get is going to correspond to it. Okay, so how did we get that type for the regular expression? How did we go from this regular expression string to this type at compile time? All right, so here's where I'm taking advantage of the fact that I'm working in Haskell. Right? So the very first step, I get to take advantage of template Haskell, which is Haskell's mechanism for compile time metaprogramming. That lets me put in a compile time parser that will translate this regular expression string to a sequence of applications of regular expression constructor functions. So each of these functions, ralt, rempty, rchars, they construct regular expressions. They construct, alternations, regular expressions that accept the empty string. And so what template Haskell does is it pretends that I had just written this application of all these functions instead of that string. It parses the string into those applications. Then, after it does that compile time parsing, then it runs the Haskell type inference. So template Haskell it's untyped, it produces its output in an untyped way, but then type inference gets to come into play. And type inference, the types of these functions like ralt, rempty, rstar, that's what calculates that the type of this regular expression for file paths captures exactly these groups. All right, so let's take a look at how that works. And I will point out that I'm using this extension called type applications. The names of the capture groups, that needs to be part of the type. That's a type level string, so I need to give that explicitly. So anytime you see an @ sign, I'm doing a type instantiation, not a normal function application. Okay, so here are these constructors, right? And so this is my library of regular expressions. It has this interface. This interface tells me about what the capture groups. So if I have a regular expression that only accepts the empty string, it's not going to capture any groups, right? All it does is the empty string. Or if I have one that only accepts a particular character, it also doesn't capture any groups. So in those two cases, my index is just the empty list, right? There are no capture groups there. What about for these combinators, for constructing alternatives, sequences, cleany star? Here I have some computation to do. And here I'm going to dispatch to some type level functions that it's going to calculate what the capture group is based on what the subcomponents are. Right? So I have some functions called alt and merge and repeat, and that's going to produce the answer for me. And then finally, where do those names come in the first place? When I have a marked subexpression for a capture group, here's where I need to say, I've seen this particular name exactly once, because I've marked it here in the string. And so I'm going to merge in this pair that says I've seen this name once with the other capture groups that I have found. So let me tell you a little bit more about what these type level functions do and how they can calculate the answer. So we're storing this capture group information in a symbol map. I'm using this list of pairs just as an association list. We can think about it as a finite map from these type level strings or symbols to the occurrence information. The occurrence information is just a standard data type that I have written that I'm able to use at the type level. This occurrence map, or the symbol map, is this list of pairs, but I'm also going to maintain the invariant that I'm storing it, it's an ordered list of pairs. I'm going to keep the symbols in order, right? Because I want to keep track of how many times a symbol occurs in a regular expression. And so I use that invariant in the implementation of merge. So merge, it's a lot like the merge function from merge sort, right? It takes two sorted lists of these symbol occurrence pairs and merges them together. And the syntax might look a little weird because I'm writing it as a type level function, but otherwise it looks a lot like a Haskell function that I might write at the term level. Thank you. So if I'm merging together two lists of pairs and the symbols are equal, here is where I'm only going to put it into the list once, into the output once. And this time when I put it into the output, I'm going to say that I've seen it many times. My type system, it's not super precise. I'm not going to count exactly how many times I've seen a particular symbol. I could enhance this data structure where I'm keeping track of the numbers. I didn't want to do length index list anywhere in this example, so I'm not being that precise. I'm going to abstract a bit in the analysis that I'm defining. Right, so if I see it once, I've seen it many times. I mean, I've seen it more than once, it's many times. Otherwise, I need to preserve the ordering, and so as well as doing a type level equality function, I can also do a type level comparison function on these type level strings and figure out which pair should go in front of the recursive call. The thing to notice about this merge function is that it's not a structural recursion on either one of its arguments. Why does it terminate? right? Something's going down, but sometimes both lists are going down. It's the tail of both lists. Sometimes it's the first one, sometimes the second one. You have to think just slightly if you're going to write this in Clock. Haskell's a little different because you don't have to prove any of your type level functions terminate. You don't have to prove any of your functions terminate in Haskell. You can't prove any of your functions terminate in Haskell. So, but that's fine. The extensions, when we've been thinking about the extensions of Haskell with these ideas from dependently typed programming, we've always done them in the context of allowing non-termination, both at the term and the type level. And the language remains type sound, even in the presence of non-termination. Right, so you can see just from this first part that GHC is a little bit different than how Coq or Agda might do, right? Many of the dependently typed languages, of course, you can write functions in types, and that's what we wanted to do. We just want to write a function that calculates that compile time information for us. It's a little bit different because it doesn't have to be terminating. There's other ways that it's different that I'm not going to get into now based on the interaction with type inference. I don't think it's the end of the story for how type-level functions, type-level computation is in GHC. I would love to see future extensions that make type-level functions in GHC more like other dependently typed programming languages. Okay, so now let's talk about the next feature of dependently typed programming. We just saw type-level computation. Now here's the next feature, which is after we've computed that data, what do we do with it? Well, we can use that data to constrain the values that we use in our program, right? And guide how that type checker works, right? And so we saw that we have this type for the dictionary, and we could access from our dictionary using this get function. And get is overloaded. And I told you that ampersand, that @ sign for E, that's a type argument. So we're using a type argument to access. So we need to know what that type is to be able to resolve that overloading, to know how to access from that dictionary, and also know how to produce that custom error message for us. Right, so let me tell you a little bit about how that works. So we're going to use a gadet to represent our dictionaries, where the index on the dictionary is going to very tightly constrain how we represent the data at runtime. So a dictionary, it's like a list indexed by this symbol map, and for every entry in that list, it's going to defer to another gadet that's indexed by the particular name of that symbol and its occurrence information at that point. Right, and so it's exactly going to line up. So because the symbol maps store all the capture groups in alphabetical order, our dictionaries are going to store all of the information associated with the capture groups in alphabetical order. We're going to know at compile time what order we're going to store that information. Now the entry itself, it's indexed by the name of the symbol and its occurrence information, but it only has the value that we need to store when we capture, that we're capturing. And we're going to compute the type that we need to store that information by using that occurrence information. So we have another type level function here that's just going to pattern match on that occurrence information and tell us at each entry in our list here what type of value we're going to store. And it's going to be one of these three types, right? Either we know we're going to get a string there, or maybe we're going to get a string there, or we have some list of strings there, depending on what our occurrence information is calculated from that type level computation. Right? And so what that means is when we see a dictionary, when we see something that has this type, we know a lot about it. We know it must be of a very particular form. Right? It must have some string for B, it must have some list of strings for D, and then it must have an optional string, a maybe string for E, for that extension. Right? And so the type checker knows at compile time the order that the values are stored, and so then we can use type class resolution to access those values with the get function. And because the type checker knows at compile time that there's not an F in there, that's how we can do a type error. Right, so the get function, here I'm using the get function I'm actually taking advantage of something that is part of the Haskell ecosystem. This is an overloaded, there's a lot of different implementations of flexible records in Haskell. And what I've done is I've essentially implemented yet another implementation of records in Haskell. But many of those, you can access those flexible records with this very general overloaded function that says that if a particular record R, so if a particular record R has a name in of type A, is that better? Oh, thank you. If a particular record R has a name in of type A, we can project from that record that value, right? So that doesn't, that works for any flexible record type. And so our goal is to produce an instance of the has type class and show that for a particular capture group N, our dictionary has a particular type A. Well, under what situations? Right? And what are the situations? When do we know? Well, I've written a type level find function that's going to look for that name in that symbol map. And if it finds it, it's going to give me a proof that it found it. It's going to, that proof is just an index. It's going to say, here is where I found it in the symbol map. And then I'm going to use the get type class to use that proof to know, to put together that accessor function, to know how many times I need to go down that list to access that value. If the find function, now this find function, you can't tell from the type, but the find function is a partial type function. Sometimes it returns a type error. And so if it gets to the end of the list, if it's looking for a particular symbol and if it gets to the end of the list, that's where it has the opportunity to produce that custom error message. All right, and so I think this is a really great example of how we're taking advantage of this information that we've computed and very much scripting how the type checker governs our access to that data, both when it works out and also when we want to report an error to the user. Right? And now all of that happens at compile time. The next feature I want to talk about is what if we want to use that data that we've gotten from that type level computation, what if we want to use that at runtime? Right? And so I'm calling this double duty data because we're using it both for specifications, both in types, but also to affect the runtime execution of our code. Right? And so where do we need to do that? Well, you actually saw that happen. So this is the code you've seen before, right? It's the definition of the dict type class. And here D is just an element of, is a dictionary. And I actually showed you one of these things. I showed you a result, right? I asked Haskell to print it out for me. And if you remember what it printed out, it kind of looked like this. So I wrote some code to print out dictionaries. It's printing out the names of the capture groups. But where are those names coming from? Those names are not stored in runtime in the dictionary, right? The entries only have the values. They don't store the names. The names are only part of the types. So the show implementation has to get that runtime information, the string for that capture group name, and it has to put that in the output. Right? And this is where people start feeling like now we're really doing dependently typed programming. I would argue that all the stuff we did before is still dependently typed. You don't have to get all the way here before you can say that you're doing dependently typed programming. But this is where pi comes in, right? And so here, if Haskell had pi, if it had a way of quantifying over arguments that let you use them in this double duty way, let you use them both in types and use them as arguments to your computation, this is the code I would write. So just for showing the entry part, and then to show the whole dictionary, I would show all the entries. Right? This is the code I would write. And you can see I need arguments not just for the name of the capture group, I also need this occurrence information so I know how to print out. So I know how to print out the values in each case, right? Because all I know for each entry, right, all I know for each entry is that it is some occurrence type. And I need to pattern match on the occurrence type to know how to resolve the show type class, to know how to print out a string, or how to print out a list of strings, or how to print out a maybe string. Now, I don't have pi in Haskell, right? So this is not the code I wrote. Let me show you the code I did write, right? I had to use a technique in Haskell that's called singletons, right? And what singletons is the ability where you create a data structure that exactly mirrors your type level arguments. And so whenever you take a type argument, you also take a singleton argument at the same time. And if you need that type argument around at runtime, you use the singleton argument instead, right? So the places where I had pi quantification, now I'm just quantifying over these singleton arguments. And when I pattern match, I can't pattern match over once, often, many. That's the type. But I can pattern match over this singleton for the occurrence, which is this data type. It's a gadet that exactly lines up. So when I find that this is s once, I know that the type argument must have been once. So it works, that pattern matching works in the same way that dependently type pattern matching does. Now, I wrote this stuff in italics because I actually didn't have to define this directly. Here I could take advantage of the singletons library to automatically define this. So I didn't have this duplication. I didn't have to write my types twice. I could let the library take care of that for me. So singletons, they have this bad reputation a little bit. Some people think that they're awful to work with. Just from this example, I'll say that singletons was not the hard part. I had the library to rely on, and when I work with singletons in this library, I can work with it almost as if I was working with a pi quantification. The fact that I have this singleton type, it's indexed for the kind, it tells me, it's kind of like a type function, but it takes a kind as the argument. It looks at this kind k to figure out what is the singleton type for this. So I can always just say singleton argument, and that tells me it's as if I had done a pi quantification. And then the other really important part from the singletons library that I'm taking advantage of is this mix between implicit and explicit arguments, right? So in Haskell, most types are supplied implicitly. We use type inference for instantiation. Occasionally you'll see that @ sign, that's an explicit instantiation. Value level arguments are the reverse. They're always done explicitly unless we have a type class to pass them in. The dictionaries in the type class is an implicit instantiation. So now when we have something that a singleton where it's mirroring a type, a lot of times we can instantiate our types implicitly, and so we would like those value level things to also be instantiated implicitly. We don't want to have to construct those singleton values when we already know what they must be. And so this class here, sing_I, it carries around the singleton values for each type. So if we can use this sing_I class can supply the singletons that we need. And this is exactly how I can get the information from the type to be able to show a dictionary, right? I have this sing_I constraint that says, look at that type, figure out what singletons I need for that symbol map that I'm using, then pass the singleton for the symbol map to the show function for dictionaries, which is going to compose it, find the singletons for the entries, and be able to show that information at runtime. So I really have this nice combination of runtime and compile time facilities working for me. Now, of course, there still is a little bit of friction, but I will say that the end is in sight. I mean, it's actually not impossible to imagine that Haskell could have a pi type very soon. So Richard Eisenberg, my student who graduated just recently, his dissertation exactly describes what we need to do to add a real pi type to Haskell. And the semantics of that pi type, we know what those are. I mean, it comes directly of how we've been using singletons in this language. Okay. Equivalence. Now, you know anybody can't talk about dependent types without talking about what equality means in that. And that shows up here in this example too, right? Whenever we are working with computation in our types, we need to type check our programs. We need to decide when things are equal to each other. And so let me show you what that looks like in the context of this implementation in Haskell. So here I'm starting to look at the implementation of this regular expression library. So if I didn't have these refined types, so say I had a simply typed implementation. I have a data type that is representing all the regular expressions, right? So it's a pretty straightforward data type here. And then I have a function. So one of the functions in my implementation, like these constructor functions that I showed you earlier, they actually do a little bit of simplification before they construct sequences. So for example, we know that if we're constructing a sequence of two regular expressions, and the first part of that sequence is the regular expression that always fails, we don't need to construct that sequence. We know that regular expression is always going to fail. So we can just return our void for that. So we can do some optimization. Likewise, if we're constructing a sequence and the first part of that sequence is the regular expression that accepts the empty string, we don't need to remember that, right? The second part accepts the exact same language, so we can drop that initial empty string. Now, what happens when we add type indices, right? So when we start keeping track of the capture groups in our regular expressions, the types of our constructors have all the same types that you saw before, right? The same types that we saw for the interface, just so they can calculate what the capture groups are. But now in our implementation, we have to make sure that our implementation functions actually respect these indices, that they have that type, right? And so let's take a look at that. Well, for the first, so down here at the bottom, the last line is very easy because I've given the type of the function the same type as RCCats, right? So the last line is easy. But let's take a look at the first line, right? The first line, we're doing this optimization where we're ignoring R2. But we do need to produce a regular expression indexed by the merge of S1 and S2. But here what I've done is the type that I've given for our void, I've said this regular expression can be indexed by any symbol map, right? Whatever capture groups you want it to capture, sure, it can pretend to capture those. Why does this make sense? How could this be some? Well, our void, the void regular, it's not going to match anything, right? So it's kind of like it's acting like a false, right? I can, if it returned a result, it would capture this, but it's never going to return a result. So it's perfectly sound for this type to give it an ultimate flexibility. And so here, our void, it can have the result type, so it doesn't even matter what's before the pattern match. What about here? So for this one to type check, right, we need a result that is merge S1, S2, but we've pattern matched R empty, and that's told us that S1 is nil. So we need the result to be merge nil S2, right? But we're returning R2, so it just has type regular expression indexed by S2. But if you remember from the definition of merge, right, if we're merging an empty list with any other list, we just get that. So by the definition of merge, we directly have that. And so this also just automatically type checks. So even though we've added this more informative type here, our code just goes right through. What about, does it always work that way, right? Can we always just use our definitions of our type functions to type check our code? So here's an example where things don't go so smoothly. So here I have R star, right? Now if you have a regular expression and it appears under cleany star, we need to take all the occurrence information and promote it to many, because we don't know how many times we're going to be using that cleany star to match our code, right? But when we create an R star, we can do two optimizations when we construct that, right? If we do the cleany star of empty, that's the same as empty. And that one, that works just fine, right? Because if we repeat not capturing anything, we're still not capturing anything. But what if we do cleany star of cleany star? That's just the same as doing one cleany star, right? We don't need to double things up, right? And here we're going to get a type error. Right here, Haskell's going to tell us this, right? You type it into Haskell, and you get this error message. It says, I can't prove this thing. I can't know that repeat S is equal to S when I know that S is equal to repeat S1. So S1, so R star, if R has type RS1, and then the whole thing has type RS, where S is equal to repeat S1. So this comes from the pattern matching. This is what we need from the right-hand side. And so really what we need to know, that repeat, this type level function, it's an idempotent function, right? Doing it twice doesn't change anything, right? And it's not true by definition, but if we were in Calc or Agda, we would just prove it. We would do it right. We would do a quick inductive proof and show that. What are we going to do in Haskell? Well, in Haskell, I'm going to do something a little bit different. Right? In Haskell, I'm going to get the type system to prove it for me. So in Haskell, I'm going to define this class, and it's a class of symbol maps that has exactly this property that I need to make my code type check. Right? So these are the well-formed symbol maps, right? And the precondition for that class, this is the superclass, the precondition is that for the symbol map to be well-formed, it has to be, the repeat function has to be idempotent for it. And I can define instances of this class. So I can say, okay, make sure that the empty list, the empty symbol map, is well-formed. And Haskell says, sure, right? It plugs in the empty list for S in this example. And now I can do the inductive case too. What if I have a symbol map that is a cons, that is this pair cons onto that? Make sure that it's well-formed. But you get to assume that the tail of that list is well-formed. And Haskell will do that inductive step for me, right? And so now I know that for any symbol map that is either the empty list or a cons, it's going to be well-formed, right? So I have this property available to me for almost every symbol map. Now, I can't do that same step by saying, okay, now you know well-formed for anything, because that's not quite true because of non-termination. But what I can do is I can just add extra preconditions about well-formedness for my symbol maps. Anytime where I quantify over a symbol map, I can say, not just any symbol map, one that has the property that I want. And once I do that, right, in R star, when I have the R star function and I pattern match here, I do this pattern match, I'm going to find that S1 is going to be a well-formed symbol map. And so that means I have this property in my context. I don't have to do anything special to use it. The Haskell constraint solver can just take that constraint out of the context and use it directly. And so I haven't had to modify my code other than adding the extra class constraints to propagate the information around. So I think that's really cool. Right? Right? I didn't have to do an equREFL or try to eliminate this equality that I've proven. The Haskell constraint solver has figured out, it told me exactly the property that was missing, and once I provided that property, it applied it right away. Now, at this point, I would love to tell you more about my implementation of regular expressions, pattern matching with submatching. But I don't quite have enough time. Andy is giving me the 5-minute point. So I'm just gonna tell you this one line, right? Which is I'm basing my implementations, a very simple implementation based on regular expression derivatives, where I do the submatching by just propagating the marks through the derivatives. The marks capture the strings directly. And then after I've done the derivative, with all the characters in a word, I can find out whether that regular expression matches that word using this extract function that tells me not only is it nullable, but it pulls out that dictionary. It pulls out all the captured strings that are stored directly in the regular expression. To make the extract function and the deriv function type check, I don't need any new features other than the ones that I've just showed you. I need a couple more properties, like the one that I showed you with about repeat being idempotent. I just added them directly to that well-formed and its predicate in the same way that I did for repeat. Okay, so we've kind of seen that GHC has a way of doing proofs in your dependently typed program. This example that I've shown you, it's not about verification. In fact, I'll come right out and say I had a lot of bugs that when I was implementing my regular expression library, none of them would have been caught by my type indices. None of them were caught by type checking. I wrote a lot of test cases, right? But we can do proofs in GHC, but we do them in a slightly different way, right? I've been tending toward compile time proofs because those are the ones that I know don't have any runtime costs and that can be verified as I compile my program. Right? GHC can do runtime proofs. Right? There is a way to use type equality proposition as a type and write term level functions that will do a runtime proofs, and those runtime proofs will look a lot more like the proofs you might see in Agda or Coq. But GHC doesn't have any of the other features that make working with those proofs pleasant, like IDE support or tactics. So I don't think that's the way to go for GHC. Instead, I think GHC should focus more on automated theory proving. Kind of like I just showed you, the fact that we need to have good ways of identifying what properties we need and good ways of teaching the GHC type checker about those properties so that it can provide them automatically, right? And so some of the ways forward, so Wilhelm Schoberg, his dissertation, he talks about congruence closure, integrating that with dependent types. There's also a way to plug in arbitrary solvers like SMT solvers into Haskell's type system. Or maybe there's a way from the verification that Liquid Haskell does, a way to integrate that with what we have. So I've shown you these 4 features of dependently typed programming, and I'm hoping to convince you like 2 things, that dependently typed programming is not just program verification. There's a lot more to it. And you can kind of think about how dependently typed programs work in a much more refined way. It's not just about having a pi. It's not just about doing proofs while you're doing programs. It's a very rich connection between compile time and runtime reasoning. Right, and then the last thing I hope that you've been convinced is that GHC is a really fun part of the design space of dependently typed programming. And it's a really good idea to take things that are working in one place and shift them over to another language just to see what you're going to get. So I'm going to conclude here and thank all of my collaborators. None of this would have happened without them. Thank you.
Thank you, Stephanie. Okay, we have time for questions now. We have some folks who've got microphones. So if you'd like to ask a question, please come out to or indicate to the mic bearers. And this applies, by the way, throughout the conference. We're recording all the talks and trying to record the discussions as well. And the questions only get onto the video properly if you actually are speaking to the mic. Okay. Is that Andrew?
So on one of your slides, you cited a 2006 paper by you and some other authors about GADTs.
Mm-hmm.
How many of the authors of that paper at the time realized that they were doing dependently typed programming?
That's a good question, and it's been over 10 years since that paper was written. I knew about dependently typed programming at that time. I really wanted GADTs for being able to do type indexed programming, which is a very specific kind of dependently typed programming. I saw GADTs as a more general mechanism, and I had seen other very similar papers that pushed, this was not, that 2006 paper was the paper that integrated GADTs into Haskell. There were lots of other people working on GADTs at that time, and they also had examples that were more related to dependently typed programming and dependent ML.
type systems are there to help programmers to detect errors, but now you are also computing with types, so you write some code to compute with types. So is there a system that helps you to discover errors when you are programming with types?
So the type level programming that I do has its own type system. So
Can you? Okay, good. What I always wonder when I do all this, do GADT programming, so I mean, I very much believe in, getting the correctness stuff, but I'm always kind of a little bit frustrated when, you have to go down a whole list using your indexing proof, or, go through your dictionary and kind of one by one, and it always feels like it's inefficient. And my question to you is, how are we going to make programming in this form like efficient? Can we make our dictionaries, do hashing on the strings somehow, or can we do, you know what I mean? There's all these data structure things, and we want to do those and also have our correctness. And is that possible, or do we have to cheat, or what's the answer?
Hello? Right. I will repeat the question. One thing that seems to come out from what you're saying is that when we originally said, oh, we can have separate namespaces, that was a really bad idea. And trying to exploit things and be clever, I think in general, is a really bad idea. So thank you for emphasizing that.
Hi. So this well-formedness type class smells to me a lot like a logical relations argument, because you're defining a relation, a type class, and then proving, or getting Haskell to prove, that every type you care about is in it. Does that seem like a reasonable analogy? And might we exploit this analogy further?